Let's jump right into this explainer because we're breaking down a seriously cool Python project today. We're looking at a setup that literally turns your smartphone into a wireless trackpad and keyboard for your laptop using nothing but your mobile browser. If you've ever been relaxing on the couch and wanted to control your computer across the room without having to download some clunky, ad-filled third-party app, well, you are absolutely in the right place. To really appreciate this illusion, we have to start with a fundamental question. How exactly does touching a piece of glass on your phone instantly control a PC across the room? And remember, we're doing this without installing any dedicated apps from an app store. Imagine just opening your standard web browser, connecting to your local Wi-Fi, and boom, you have full control of your machine. It honestly feels a bit like magic, but the entire backend powering this whole shebang is actually just written in Python. So here's our roadmap for how we're going to deconstruct this. We'll cover 1. The wireless trackpad project itself. 2. The dual server architecture. 3. Real-time WebSocket communication. 4. Translating data to actions. 5. The complete system running. And finally, 6. Building beyond the mouse. Starting off with Section 1. The wireless trackpad project. Let's track the journey of a single screen tap. It all starts at the phone browser, which fires a request over your local Wi-Fi network. That signal drops straight into a Python backend running locally on your laptop, which then turns around and talks directly to your operating system to finally act as a physical cursor movement. This high-level architecture is brilliant because it neatly separates the simple job of loading the user interface from the heavy lifting of handling your live, rapid-fire finger swipes. Let's move to Section 2, the dual server architecture. To manage all that network traffic without bottlenecking, we actually run 2 separate servers. First, we have an HTTP server running on port 8000. Think of this just like a restaurant hostess handing you a menu. Its only job is to serve up the basic HTML, CSS, and JavaScript interface to your phone. Completely separate from that, we have a WebSocket server running on port 8765. This acts as your highly attentive waiter, exclusively dedicated to taking and executing your real-time screen taps. Now, because we absolutely need both of these servers running at the exact same time, the project utilizes Python's built-in threading library. This allows these 2 distinct servers to operate in parallel without blocking each other. So instead of freezing up your entire application while waiting for a web page to load, Python just spins up a background thread for the HTTP server. That way, the main program stays laser-focused on listening for your real-time commands. Which brings us to Section 3, real-time WebSocket communication. This right here is the absolute heart of the project. Unlike standard HTTP requests that have to constantly open, request data, and then close down every single time you tap something, WebSockets create one permanent, persistent connection. This low-latency bidirectional highway is absolutely vital. I mean, if you're continuously dragging a finger across your phone screen to move a mouse, you literally cannot afford the delay of opening and closing connections. WebSockets keep that line wide open. But dealing with an open fire hose of constant data requires a special approach, right? To handle those rapid WebSocket messages smoothly, the project utilizes the Async-Licky library, which introduces a really cool concept called an event loop. Instead of stubbornly waiting for one message to be fully processed before looking at the next, the event loop efficiently juggles multiple operations at once. This ensures that even if you're frantically swiping and tapping, your Python application isn't going to freeze up or drop your commands. Let's look at Section 4, translating data to actions. So how does Python actually do it? Well, a tiny JSON payload sent from your phone's browser gets mapped directly to a concrete operating system action. For instance, if the server receives a payload specifying a type of move alongside delta x and delta y coordinates, a Python library called PyNedit instantly converts that into a literal, physical, pixel-by-pixel shift of your mouse pointer. We aren't sending raw, complex hardware codes over the network. We're just sending beautifully structured JSON. The Python server is continuously checking the type field of these JSON messages, acting basically like a rapid-fire switchboard. Depending on what it reads, it can trigger a massive variety of actions. It can distinguish between a left and right click, manage press and release events for dragging a file, take scaled values for smooth scrolling, or even execute complex multi-key keyboard hotkeys like Control-C or Alt-Tab. And here is a fantastic programming best practice. Rather than sending raw, messy hardware codes over your Wi-Fi, the project uses a special keys dictionary. So when your phone simply sends the text string enter, this dictionary intercepts it and cleanly maps it to the exact OS-specific keyboard object required to press the enter key. It's a small detail, but it keeps the communication code so clean and infinitely easier to maintain. Moving into Section 5, the complete system running. Now, anyone who has done local networking knows the biggest friction point is usually finding your IP address. Instead of forcing the user to dig through their computer's system settings, this code intelligently uses Python's built-in socket library. It connects to the network interface, automatically detects your exact local IP, and simply prints the URL you need to type into your phone right there in the terminal. It is a massive, massive upgrade for usability. Pulling it all together, the main function executes this really elegant boot sequence. First, it displays that local URL for you. Second, it starts up the HTTP server in a background thread so the UI is ready to go. And third, it launches the asynchronous WebSocket server to wait for your inputs. And remarkably, it handles client disconnections gracefully. If your phone's screen goes to sleep, it safely exits the communication loop and just waits for the next connection, without crashing the whole app. Let's wrap up with Section 6, Building Beyond the Mouse. Because this system is built in such a modular, decoupled way, it's incredibly easy to expand. You could easily inject some new logic to handle file transfers between your phone and laptop, add dedicated UI buttons for media and volume controls, sync your clipboard text, or, and this is my favorite, generate a QR code right in the terminal so you don't even have to type the IP address, just scan and connect instantly. I absolutely love this takeaway from our source material because it really hits the nail on the head. It perfectly captures why deconstructing this specific project is so valuable. You aren't just learning a fun party trick here. You are deeply learning the architecture of how modern applications, web browsers, local networks, and operating systems all communicate to create a seamless, cohesive experience. Ultimately, by building what looks on the surface like a simple remote control, you've actually unlocked a complete toolkit of intermediate Python concepts. Instead of learning about asynchronous event loops, multi-threading, or JSON communication in boring, isolated textbook tutorials, you've combined all of them into a real-world, highly responsive solution that you can literally touch and feel working right in front of you. We've seen exactly how these software components communicate seamlessly over a local network to turn a plain piece of glass into a powerful controller. The foundation is laid. You know how to serve the interface, capture the data, and execute the actions. So the only question remaining for you as a developer is, how will you apply these powerful concepts to build your own incredible real-time user experiences next?